So this is a video about band theory, or another way of putting it would be electron energies in solids. So this relates to the line spectra topic, and I just decided, although I'd said you could work on this independently, since I've made videos anyway, I may as well make one more. So here's one more on band theory. So the section says band theory, and if I read through the points, I'm going to summarise them really easily afterwards. So it says, appreciate that in a simple model of band theory there are energy bands in solids. So we're going to start by trying to explain that. Understand the terms valence band, conduction band and forbidden band, or the band gap. Then C, use simple band theory to explain the temperature dependence of the resistance of metals and of intrinsic semiconductors. And then D, use simple band theory to explain the dependence of light intensity of the resistance of an LDR. Now, if I were to sum all of this up, really, band theory is about why things conduct. So why things conduct electricity, some things conduct electricity and others don't, and how we can affect the conductance of some things, like semiconductors, that under certain conditions change the amount they conduct. And we briefly touched on this when we talked about LDRs and also thermistors back in year 12. And you may have talked about it a little bit more with Mr. Martin when you did operational amplifiers and how when they used as comparators. So let me just take us back first to line spectra. So what we're really talking about here is why do things conduct, and it relates to our quantum physics of gases and line spectra. So I'm going to look at that first. So if you remember, this is a picture of not a line spectra but an energy level diagram which allows us to find the lines produced. So a drop of an electron energy from here down to a lower state, maybe this is the ground state, that drop of energy produces a photon, and that photon has a particular frequency and wavelength. A line would be produced that we could visibly see, but these are not those lines. These represent the energy levels that happen in electrons. Now, these electrons, as we said at that time, are in gases, which means they are very isolated from each other. They are able to receive energy quite separately from each other. And as a result, these are the lines of energy levels that electron could exist on. Now, what we're saying is that these electrons are in atoms that are totally separate from each other in gases, and this is not to scale at all. If there's big gaps in between like this, any energy received by this atom and this electron is not received by this one, and it's not passed by this one onto that one. That would take an extreme amount of chance for that to happen, where they have to bump into each other or something. But that's not the case in solids. A solid is like this, isn't it? Where all of particles are in fact touching, if it's possible to touch it all. Remember, they're mostly space. So if I shine light on this, or I heat this up, and this electron here receives energy and it's moving around, it can easily transfer that energy to these other surrounding electrons. And so although it can exist on an energy level, seemingly, when its energy can be passed on to other electrons quite easily, suddenly the amount of energy levels that it could exist on becomes a lot more. So if I go to the textbook now and look at the diagram in there, so I'm looking at this one here, we are imagining, and suddenly there's lots of lines that it could be on, instead of just one or two that have big spaces between them. So there's suddenly lots and lots of energy levels, and that then can be approximated to a much more continuous energy range. So instead of what we had before, which was this electron can either be on 3.4 electron volts, or minus 1.5 electron volts, sorry, minus 3.4 electron volts and minus 1.5 electron volts. We're saying that that electron could be anywhere between 3.4 and 1.5. That there are so many lines in between here that it's a range now that's virtually continuous up to a point. So we are approximating this many lines to actually just like a band that it could be in, it could exist in any of these things. But there are areas and there are values that it cannot exist on. So this might be, let's say that's 3.4 there, sorry, let's say that's 1.5 there, that there might be an area where it cannot exist between 1.5 and say 0.4 or something like that, that it can't exist there, but from 0.4 onwards to another range, it can exist. So there are some areas where it absolutely cannot exist, that the energy levels between the individual atoms make it impossible for it to be on that level, on those levels. And there are some gaps there, and we call those forbidden gaps. So forbidden gaps. Okay. So one question that is in your pack over here, and that's the area we are right now. It's saying some of the electron energy bands in a solid are illustrated. So forget about these words over here for a moment. It says in isolated atoms, electron energy levels have discrete values. So that's line spectra. Okay, so don't get confused. That's line spectra because it's isolated atoms. Suggest why in a solid there are energy bands rather than discrete energy levels. What we would be talking about here then is that in the solid that there are lots of atoms that are very close together, that are touching each other in fact, and this changes their energy levels as a result because the energy can spread from an atom to atom, and so we end up with a spread of energy levels in a band. So I gave you the mark scheme, but you could simply say that in a solid the atoms are very close together, 1 mark, that this changes their electron levels, 2 marks, which now causes them to spread those energy levels into bands. And according to the mark scheme, that's good enough. But let me put it in a more plain English way then for you. So it might make sense. In solids, atoms are touching, their energies can be passed from one to another, passed from let's say from neighbouring atoms. Changing the atom's electron energy levels spreading the possibilities into a continuous band. Okay, so there we go. If you want to pause the video and read that through, that is fine, and that should get your 3 marks.